Recursion is a very important concept for data structures and algorithms, and we'll be using it throughout the rest of this course. It can be pretty difficult to wrap your head around, so I think it's best to introduce this topic as soon as possible. We're going to start with what I call one branch recursion, and we're going to do so using a math formula, specifically n factorial. If you're not familiar with it, n factorial is a shorthand of writing n times n minus 1 times n minus 2 all the way until we get to the base number, which is 1. So for example, to say 5 factorial would be to say 5 times n minus 1, so 5 minus 1, which is 4, and then n minus 2, which is 3, and then keep decrementing the number by 1 until we get to the base number, which is 1. And then, we do this calculation, it turns out to be 120. Now, you definitely don't need recursion to do this calculation. The easiest way to do it would be with a loop, where we take this number and then decrement it by 1 and multiply it by the result until we get all the way down to 1. But we can also do this with recursion, and I think it's a good way to get introduced to recursion. Notice how 5 factorial is the same as 5 times 4 factorial, because we know 4 factorial is going to be 4 times 3 times 2 times 1, and we see that repeated over here. So another way of representing 5 factorial is to say 5 factorial is equal to 5 times 4 factorial, or the general equation, which we've written up above, would be to say n factorial is equal to n times n minus 1 factorial. The reason it's important to understand it in this way is because recursion is all about subproblems. We can see that it's not super simple to calculate n factorial, but we know it's going to be n multiplied by n minus 1 factorial. So we took a big problem and made it a slightly smaller problem. We call this the subproblem, and this is why we're allowed to use recursion for this problem, because we have a subproblem. Now, I could show you what the code would look like to solve this recursively, and it's actually very short, but I think it's better to start with a visualization and then move to the code, which makes it easier. So suppose we're trying to compute 5 factorial. We know that the subproblem is 4 factorial n minus 1, right? So we take 5 minus 1 and we want to compute 4 factorial first. So suppose we want to compute 5 factorial. We know that the subproblem we have to compute first is 4 factorial, and then we can multiply that by n, which in this case is 5. By far the best way to represent recursion is using a decision tree. In this case, we only have one decision. That's why I call this one branch recursion. But a tree is still helpful to visualize this. So before we can compute this, we have to compute 4 factorial. So in terms of code, this step would look something like this, where we have a function called factorial. It's going to take in some integer where we're going to compute the factorial of that, and then we're going to return the result, which is also an integer. Now, so far we know that to compute n factorial, we have to solve the subproblem, which is n minus 1 factorial. So we call the function that we're inside of. We call our own function. We call the same function. This is called the recursive step. But this isn't all we need. That's why I've left a little space over here. So let's continue with this and see what happens as we continue to solve the subproblem. So we have 4 factorial. Well, again, we know that's equivalent to 4 times 4 minus 1 factorial. So we want to compute the subproblem 3 factorial before we have 4 factorial. But the same applies for 3 factorial. It's equivalent to 3 times 3 minus 1 factorial, which is 2 factorial. So let's compute that. And again, same applies to 2. It's equivalent to 2 times 2 minus 1 factorial, which is 1 factorial. Now this is where we get to something different. Once we get to a 1, that's the base of our series. That's the last term of the multiplication. So when we get to 1 factorial, that's equivalent to 1. So that's what we call our base case. That means that for 1 factorial, we're not going to use this formula because we assume that 1 factorial is mapped to a constant, which is 1. So we don't have to do this calculation because it would result in 1 times 1 minus 1 factorial, which is 0 factorial, which in math is valid. 0 factorial would also map to 1, but that's not so important for our case here. What's important here is that 1 factorial is when we can stop. So in terms of code, that would look something like this. If n is less than or equal to 1, we can return 1. The reason I say less than or equal is because of that 0 case. If we were given 0 as our original input, we would want to return 1. That's just the definition in math. But you can see this is very important because if we don't have this, we would continue this infinitely. We would continue to call the same function that we're inside of. It would never stop, and we would never go back up to compute our original result, which we were trying to do was compute 5 factorial. We would never go back here. We would just keep going down and keep getting more negative and negative and negative. So how is this actually going to run? Well, let's say we were given 5 as the input. 5 is not less than or equal to 1, so we say that we're going to return 5 times 4 factorial. So that's how we go down here. We're going to go down a step to here. And then for 4, we're going to see the same thing. It's not less than or equal to 1, so we're going to compute 3 factorial. So we're going to keep going down and down and down until we get to 1 here. So that's going to be our base case. That's when this is actually going to execute. We're going to end up returning 1. So we're going to go back up to our parent and have a 1 that we're returning. So at that point, this code is going to execute. We passed in 2 minus 1 factorial here. This return call evaluated to 1, and currently n is 2, so this is going to be 2 times 1, and then from here we're going to end up returning 2. So from here we pop back to the parent and return 2. So then this line is going to execute because what we passed into here was 3 minus 1, which was 2 factorial. We know 2 factorial now is equal to 2. That was the return value of this. So then we're going to call 3 times 2 and then return that. That's 6. So now it's starting to get a little interesting. We're going to return 6. From this line, we're going to return 6 back up to the previous call. So this, which was 4 minus 1, which was 3 factorial is 6, multiplied by n, which in this case is 4. So 4 times 6 is going to be 24. We're going to return 24 up to the previous call. And then we'll know that 4 factorial was 24. N in this case is 5. So 5 times 24 is 120. That's going to be the result of the call, which is 5 factorial. So when we called factorial and passed in 5, this is going to be the result. N is 5, so 5 times 24 is 120. That's going to be our result. So when it comes to analyzing the time complexity, it can be difficult to determine just by looking at the code. That's why drawing a picture like this can be helpful. You can see that to compute n factorial, we basically have n steps. We have n calculations that we have to do, n multiplications rather. So to compute this, the time complexity is big O of n, where n is of course the input that we're given. This is the same as it would be if we used a while loop or a for loop, where we start with n and we decrement it by 1 each time to get this computation. So there's definitely no benefit in this case of actually using recursion. I'm mainly doing this to teach you, and actually in this case the recursive solution is actually worse than doing it with a while loop, because in this case we end up needing extra memory. This solution actually has big O of n memory complexity. We care about time complexity, but we also care about memory complexity. We'd rather not allocate additional variables that take up extra memory if we don't need to. Now in this case, we're not even allocating any major variables. We don't have any arrays or linked lists or anything like that. So why is this taking up O of n memory? The way this code is going to run is similar to how I've drawn this picture. We're going to have a function that's computing this. That function is going to take up space in memory, and it's going to we're going to save that. We're going to put that function on hold, and we're going to say, okay, stay right there. First, we have to compute 4 factorial, and then we're going to keep this in memory as well. We're going to save our spot here, and we're going to say before that compute 3 factorial, before that compute 2 factorial, before that compute 1 factorial. At the point where we're here, where we're calculating 1 factorial, we're going to have all 5 of these functions taking up memory. Now, each function doesn't really declare any major variables, but each function is going to have its own input parameter. So you can think of the function declaring 1 variable at the very least. And the function itself actually takes up a little bit of memory so that it knows when this function is done, return back up to the parent. But that's getting a little too into the details. The important thing here is that we have n function calls that are all going to be alive at the same time, so this takes O of n memory. And by the way, the non-recursive solution would look something like this, where we just have a single variable. Let's call it our result or our factorial. It can be initialized to 1 because we know that's going to be the base case anyway. I don't think negative factorials are something that we actually have to consider. So we're going to assume that n is always greater than or equal to 1. And then while n is greater than 1, we would multiply the result by the value, so n, and then decrement it by 1. So then we would get, n minus 1, n minus 2 until n is equal to 1, and then we would stop.